Hi, I'm Hamid Zohouri, the Director of Product at EdgeCortix Inc., and today I'm excited to demo the Dynamic Neural Accelerator F-Series AI engine along with the MERA compiler software toolkit designed for real-time deep neural network inference on FPGA-enabled edge servers and embedded devices. The DNA F-Series are a group of specialized IP based on EdgeCortix's Dynamic Neural Accelerator AI processor architecture. It's designed for deep neural network inference on Xilinx MPSOC and ALVEO FPGAs, optimized for high-resolution streaming data. Today, we will demo the DNA F200 AI engine that delivers 3.7 TOPS running at 300 MHz on ALVEO U50 FPGA card and can be deployed easily with Docker containerized environments on edge servers. Our software toolkit, the MERA compiler, which supports Apache TVM frontend, is provided along with all DNA F-Series products and enables seamless porting of deep neural network models written in standard machine learning frameworks like PyTorch and TensorFlow Lite. It also has a built-in interpreter and simulator, enabling hardware-less performance evaluation of pre-trained neural network models. From the point of view of a typical machine learning engineer, only 3 simple steps need to be taken to run a model on our DNA accelerator IP. The first step, which is completely done within the machine learning framework, is to take the pre-trained FP32 model and calibrate and quantize it to int8. Then the input resolution is specified and the quantized model is built using a single MERA API call. At this stage, we can also specify the target for deployment, which could be our built-in interpreter or simulator, or the actual DNA hardware accelerator. This creates a deploy directory with the compiled artifacts, which can then be executed on the chosen target using Python or C++ applications. Let's now look at a few demos of running DNA F200 on the ALVEO U50 FPGA card. This figure shows an example setting for real-time vision applications with DNA AI engine. High-resolution inputs are provided directly from the camera connected to a host system running the Ubuntu OS. The results of the deep neural network inference are displayed on an external monitor also connected to the host system. The DNA F200 AI engine is running on the Xilinx ALVEO U50 FPGA connected via PCIe to the host system. The DNA F100 and F200 AI engines are available as prepackaged Docker containers and can be easily deployed on-premise edge servers with ALVEO FPGAs or on Xilinx Zyng UltraScale Plus FPGAs for embedded applications. Now let's look at 2 vision applications using this setup. Here we have a demo of depth estimation using inputs from a monocular camera. The model used is called MonoDepth with 40 megabytes of model parameters post-quantization, making it a fairly large model which will not fit on the FPGA on-chip memory. This model is compiled with the MERA compiler and the FPGA is running the DNA F200 AI engine. Now let's start the video. As we can see, the model correctly recognizes the distance of different objects from the camera. Faraway objects are shown in blue, while nearby objects are shown in yellow. We observe that despite large inputs and model size, we can get real-time performance without degrading the accuracy. Note that the DNA F200 AI engine is running at 297 MHz in this case. Since the model here is 40 megabytes in size and does not entirely fit on the FPGA, the MERA compiler efficiently manages data movement between the FPGA external DDR memory and its on-chip memory in order to minimize overhead, which directly results in the real-time performance. Now let's look at an object recognition demo using a different model within the same setup. Here we have a typical MobileNet SSD object detection model compiled with the MERA compiler, which is trained to recognize people. The camera is capturing HD resolution images and feeding them in a streaming manner to the FPGA. That is, the order and the sequence of the images is maintained. In this case, all the image processing happens on the FPGA with the DNA F200 AI engine. Now let's start the video. As can be seen, DNA enables maintaining the inference latency low, especially under the streaming data conditions. We can observe that even with large megapixel data, in this case HD resolution, we can achieve accurate and low latency object detections. As the model parameter size is 4 megabytes in this case, the MERA compiler can fully utilize the on-chip memory on ALVEO U50. Since DNA F-series supports diverse neural network operators out of the box, other similar vision applications can be readily deployed using PyTorch or TensorFlow-like as well. Our DNA IP is also available for Xilinx Zyng UltraScale plus MPSOC devices. The image on the left shows how our IP is integrated into such systems to directly perform inference on frames captured from a camera and display the output on a monitor. The image on the right shows such setup. Now let's look at the setup in action. As seen in the recording, a Xilinx ZCU104 board is used in this case to perform full HD resolution video-based object detection with all image rescaling handled by our IP on the FPGA and display the output on a monitor. The inference speed is also shown in the output. Our compiler is designed to automatically interact with the host ARM CPU on board the SoC to handle other pre- and post-processing of images. In this case, the inference speed is around 45 frames per second, and the end-to-end speed is around 25 frames per second. The speed difference here is the result of extra latency imposed by pre- and post-processing operations. In summary, today we demoed the Dynamic Neural Accelerator F-series AI engine and the MERA compiler, which are currently available for FPGAs, enabling high-performance computer vision applications on edge servers and embedded FPGAs. I thank you for your time, and here are a few links you can use to learn more about DNA F-series products or evaluate them for your end applications. If you're interested to discuss specific applications, please feel free to reach out to us at our exhibition kiosk. I'm looking forward to engaging with you further and taking your questions. Thank you.